So I'd like to start with just a little bit of background. As we've been hearing about in this workshop, there's a very large range of interesting physics we can access with Rydberg interactions. And in my group in Wisconsin, we're looking at a couple different topics, mainly motivated by applications to quantum information physics. And I'll tell you about the work today together with Thad Walker on quantum gates. We're also looking at developing optical traps that will work for both ground state atoms and Rydberg atoms. We're starting towards putting a number of these together to make an atomic qubit array. We also have a project where we're looking at collective encoding, where we take advantage of the multiplicity of levels in more complicated atoms like holmium to encode a whole quantum register in one cloud. And we've also been thinking about things like hybrid qubit interfaces, coupling atoms to superconducting qubits using Rydberg interactions, and something that's not quantum information, using Rydberg mediated interactions that are non-local to create novel nonlinear spatial structures. So there's a whole range of things, and this is just the things that we're thinking about in my group, that are all mediated by the Rydberg interaction physics. And it's maybe useful to take a step back and just look in a particular way at what's so powerful about Rydberg atoms for quantum information. So here I've plotted the interaction strength of two atoms as a function of their separation in frequency units. And if we consider two ground state atoms, they have a 1 over r to the 6 van der Waals interaction, which is exceedingly weak, out past 1 micron. There's a somewhat stronger magnetostatic dipole-dipole interaction between ground state atoms that scales as 1 over r cubed. But that's still, if I'm at a micron or more separation, that's still very small, less than 1/10 of a hertz. If we excite those same atoms up to a Rydberg level, here 100s in rubidium, then at short range we have a resonant dipole-dipole, 1 over r cubed, that transitions over to a van der Waals interaction, 1 over r to the 6. And the point I want to emphasize is that the difference in these two interaction strengths is 12 orders of magnitude. So the combination of something that's very strong and can coherently be turned on and off with that much contrast is really a great feature of Rydberg atoms, and I think that's part of the explanation why you can do so much quantum information with these things. It's maybe interesting to compare the 100s interaction with the Coulomb interaction of two charged atoms. If we're here at short range, we're actually within a few orders of magnitude of the Coulomb interaction, and the Coulomb interaction is, of course, what's used to do quantum information with ions. And the trapped ions certainly are the gold standard in quantum information these days. Recent results from Rainer Blatt's group in Innsbruck are approaching 3 nines of fidelity on quantum gate operations. So it's spectacular progress, and I'm sure we'll see a lot more progress in the years to come. But there is the feature that you can never turn off this Coulomb interaction. The charges are always there. And I think the fact that it's always on does not make life easier for them when it comes to putting a lot of these together. And so it'll be interesting to see if we can take advantage of this on-off capability with the Rydberg atoms to maybe enable us to scale up more easily. And so we'll see how that goes. So with that little bit of background, what I want to tell you about today is some background about neutral atom quantum gates, how we're doing quantum gates with Rydberg blockade. I'll then talk about these ground and Rydberg traps we're working on, and finally talk a little bit about a proposal taking advantage of asymmetric Rydberg interactions. So there's a number of ideas available for doing quantum gates between neutral atoms. And the first ideas were published around about 1999. There was this work from New Mexico using short-range optically excited dipoles to do quantum logic gates and lattices. Then the work from Innsbruck on using ground state collisions to create entanglement of atoms. Neither of these proposals have been demonstrated in a single atom or two atom setting, but this collision-mediated entanglement has been seen in multi-atom experiments. So there's this work from Garching in the early 2000s, where they used collisional effects in lattices to demonstrate multi-atom entanglement. There was also more recent work from Nist-Gaithersburg, from Phillips and Porto, where they demonstrated controlled exchange interactions. So these are quantum entanglement experiments using short-range interaction properties of neutrals, but done in a many-body setting, not done between single atoms creating gates. And the idea we're following is this paper that everyone here will know about for doing Rydberg gates that's 9 years old now. And so The basic idea is we have a control atom that we can excite or not excite. If these pulses are off resonant because the control atom starts in this ground hyperfine state, then a 2 pi rotation of the target will give us a pi phase shift. On the other hand, if the control atom is in the level that is Rydberg coupled, then the dipole-dipole interaction will block this rotation and we'll get ideally 0 phase shift. So that's a controlled phase gate that we can convert into a controlled NOT gate. It's useful to understand how the error scalings work in actually realizing this. I mean, that's an idealized picture. How well can it work in practice? Well, the main errors come from 2 effects. One, we're putting population in the Rydberg state for a certain amount of time, and these are not stable states. They have radiative decay, so that gives us an error that scales as the 1 over the radiative lifetime, and then the characteristic time, which is 1 over the excitation Rabi frequency. And then the interaction is not infinitely large, so there is some finite excitation probability, and that gives us an error that scales like this, residual excitation error. If I minimize the sum of those two, I find an optimum Rabi frequency and a gate error that scales in this way. So the minimum gate error scales as the product of the dipole-dipole interaction, or blockade shift B, times the radiative lifetime. And so if we put in numbers, n equals 100, 10 microns, we get about 25 megahertz, 300 microsecond lifetime. The error looks very good. So you can just very simply estimate that this looks promising. So we have an experiment set up to do this, and the people who have been working on this currently and in recent years are shown here. The current experimental team is a postdoc Shanli Zhang, Larry Eisenhower, and Alex, who evaded my camera. And I'd like to emphasize that this is all the way through being a really close and fruitful collaboration with Thad Walker, where we've been collaborating not just on the experiment, but also on a lot of different aspects of Rydberg physics, understanding how to put this together as we go along. So there's an experiment to do this, and we need a lot of different laser systems to exert all the control we need to do these gates. And so we have a magneto-optical trap and corresponding laser systems, also for optical pumping. We have laser for our optical traps, which is a fiber laser. We have a microwave modulated diode laser for doing ground state Raman transitions, and then a 2-color laser system with very narrow line widths. These are 100 hertz line width lasers for doing the Rydberg excitation. Everything is fiber coupled to the experiment, and then there's little blocks like this and this and this, which are acousto-optic deflector-based beam positioners, so we can point at different atoms. There's actually a lot of optics hidden in those little boxes there. So it's a fairly complex setup, but it's kind of, you need all these bells and whistles to do this. So going towards a quantum gate, the first thing we need is to make sure that this blockade interaction is working. And we do that in this 2-site experiment where we have 2 optical dipole traps. This is a 1064 nanometer fiber laser. The laser is focused to about 3 micron wastes, and there's 2 spots are separated by about 10 microns. So we can load single atoms into these traps, and if we average over about 150 pictures, we can map out the spatial distribution and see where the atoms are located. These traps are very elongated. They have an aspect ratio of about 10:1. The picture is taken from the side, so we see these elongated distributions. We then apply 780 and 480 nanometer beams and are counter-propagating geometry to do Rydberg excitation or ground state pulses on these atoms. So in a little more detail, when we do the excitation for these blockade experiments, we first optically pump into the m equals 2 level. We turn off the optical trap, excite up to a d5 halves level to a particular m sub j state, and then we turn on the trap again. The trap light photoionizes an atom here before it can radiatively decay, so we use trap loss as our measurement of successful Rydberg excitation. So in the experimental sequence, we drop the Fort optical trap for a certain time and apply a variable length pulse on one of the atoms, and you see these Rabi oscillations between ground and Rydberg levels. And this just shows that we can do this at the targeted site and almost nothing happens at the neighboring site. So we have good spatial localization. You notice it doesn't come down to 0 here. We don't get full excitation. Part of this is detection efficiency. The ratio of photoionization rate to radiative decay rate is not infinite. Part of this is Doppler broadening, and part of this is just state preparation errors. So we can then do this in 2 sites, where we first excite the control atom, variable length on the pulse on the target, and then bring the control atom back down and see what we've got left. This is the experiment. So this is the target atom with no control. This is the target Rabi oscillation with no control atom. It goes up to the Rydberg and back down. If we first excite the control atom, then the excitation is largely blocked. You have this kind of eye diagram. This is a Monte Carlo simulation that takes account of all these imperfections I just mentioned, and we have indeed good agreement. And as Pierre just described, there's closely related results from the Paris groups, and they also did something additional where they observed this root 2 collective speed up, which we cannot so easily access in our setup. So that's blockade. How do we go from blockade to quantum gates? Well, if you open up Nielsen and Chuang and look, a standard way of doing that to realize a CNOT gate, if you have a controlled phase, is to sandwich the controlled phase between pi/2 rotations on the target atom. So that's a standard way of doing it, and indeed we could do that. First, we're going to now work with the m=0 states to have better insensitivity to magnetic field noise. We've previously measured about a 1 millisecond coherence time using these states, and certainly over the 10 microsecond duration of the gate, we have very high contrast Ramsey fringes working with the m=0 states. So that's one possibility, but we didn't do it that way. That's not the only possibility. We actually decided to go a different route, which is sort of a direct implementation of a controlled NOT using what I would call an amplitude or controlled amplitude swap operation, which was first proposed in the context of qubits in rare earth doped crystals by a group from Lund, Sweden. And the idea is shown here. I want to implement this controlled NOT operation, have a control and a target atom, where I couple one level that I'll call 0 to the Rydberg state and not the other level. If I put the control atom up in the Rydberg level, that blocks all of these subsequent pulses because of a blockade shift, and nothing happens to the target. On the other hand, if the control starts in 1, then these 3 pulses serve to swap the amplitudes in the ground states. So this combination here gives me a controlled NOT gate with an overall minus sign that really doesn't matter. In the experiment, we actually do it slightly differently because we had some noise issues with this laser going to the other hyperfine state, so we simulated this using additional ground state swapping pulses. So we actually have 5 pulses over here, and that gives a slightly different matrix. There's some one-atom phases that are different. They can always be corrected. So we implement this in this way, and we're going to use the 97D 5/2 states. So the implementation is shown here. We have these 2 sites. We have our ground state rotation lasers that are detuned quite far from the P level. Our Rydberg excitation is only about 1 gigahertz away from the P, and then up to MJ = 5/2. We can drive ground state rotations at 0.8 megahertz. We're driving Rydberg oscillations at about 0.7 megahertz. Then we have the following sequence here. Let me just walk you through that. We do atom loading. We do a number measurement to check that we have 1 atom in each site. We optically pump, and then we select our input states for different experiments. We run the CNOT pulses, and that corresponds to about 7 microsecond in time. And then the rest of this is to select which output state we want to measure, and then do a state-dependent measurement. The entire cycle time is about 1 second, but the actual gate is quite fast. The rest of this is reloading and magnetic field ramps and so on. So the first thing is to check our state preparation. That is, we try and prepare the 4 different possible input states, and we measure what we actually get, and that gives us this population matrix. And the fidelity in terms of the populations is about close to 85%. Most of this fidelity error is really just atom loss, and that if we look at the average of these high guys, which should be 1, compared to the background noise, that ratio is about more than 30. So that's a very good ratio, but we do have some extra atom loss when we go into these in and out of the Rydberg levels, and that gives us this 83%. We then do the CNOT pulses, and we get this matrix for the CNOT gate. So this looks like a CNOT matrix. We can again calculate the fidelity just based on these populations, and it's a little bit worse than here, but 73%. And again, we have a good ratio between the high and the low elements, about 25 to 1. The main errors are excess loss, and I'll come back to that in a moment. So this certainly looks like a CNOT gate. However, is it really a CNOT gate? Is it just some classical operation, or is this a CNOT gate we're seeing here? And one of the main points about CNOT gates is that they let you create entanglement on demand. And so to do that, before the gate operation, we apply a Hadamard or pi/2 rotation on the control atom. And if we do that with the target in the 0 state, we create this entangled output state, that is one of the Bell states. And if we start with the target atom in the 1 state, then we would create this other Bell state combination. So we do these experiments, and we look at the outputs we get, and we see the following results. So in this case, we create some approximation to 0, 0 plus 1, 1, where these high columns should ideally be at 1/2. So if I take the sum, we're again close to 70%. And this one also looks similar to what we would ideally like to get, again with a sum close to 70%. Now the crucial question here is, are these really entangled states or not? Are they just classical superpositions, or are they entangled? So let's discuss that a bit. So if I take our data and plot it just in terms of the probabilities or the diagonal elements of the density matrix, one can certainly say that there's no separable pure state decomposition that could explain our data. However, what one needs to verify is that we can exclude classical correlations. So the criterion for entanglement is that I cannot write the density matrix in this form as a probabilistic superposition. And I can't exclude that possibility if I only look at diagonal elements of the density matrix. So for example, I could construct a separable density matrix as this probabilistic sum of both atoms being in the upper state and both atoms being in the lower state. That would give diagonal density matrix elements that would look just like what we're trying to create here, but would not be an entangled state. So we need to look at the coherences to say whether or not we have entanglement. And so to do that, one can look at parity oscillations. The most general bipartite or 2-qubit density matrix can be written in this form: populations on the diagonal, coherences off diagonal. And it's not hard to show that if we define a fidelity in this way, using these 3 elements of the density matrix, then there's a very clear boundary between separable states and entangled states. If this fidelity is less than 1/2, it's a separable state. And if it's between 1/2 and 1, we have an entangled state. And this dates back to work from more than 10 years ago from the Boulder group with trapped ions. So in our experiments, we have P00 plus P11 is 0.67. So we need this coherence to be greater than 0.17 to cross the entanglement boundary. How do we measure that coherence? Well, we can do that by parity oscillations. If I define the parity as this sum of the populations, then we prepare our control atom in a superposition, we do the CNOT gate, and then we drive the same rotation on both atoms. So these are 1-qubit operations applied to both atoms with a pulse area theta and a phase phi. And if I calculate what happens, the parity evolves in this fairly complicated way. Say I choose these rotation pulses to have a varying pulse area but fixed phase, 0 phase. Then the parity would evolve in this way. So it's the initial parity times co-squared of the pulse area plus some additional terms. And indeed, we see something consistent with our data. But this does not let us unambiguously extract the coherence because it depends on some other coherences and we don't know what they are. So more useful is to put the pulse area fixed at pi/2 and vary the phase. And we vary the phase by varying some timing in our experiments. And if we do that, then the parity should evolve in this way, depending on C1, C2, these 2 density matrix elements, and the phase of the C1 here. So we do that measurement, and then we can do a curve fit of this formula to the measured parity data, and we can extract the C2 coherence, the C1 coherence, and the phase. And if we do that, our fidelity is just over the boundary. So we can say that we're within the error bars of being entangled or not. We're close to the entanglement boundary, just slightly above it. Now, notice there's this funny phase. The phase of the coherence came out to be 3.2. Let's take a look at that. Ideally, our Bell state density matrix, based on the gate matrix I showed you, should look like this. What we've measured is these populations, some very small phases here, and the 0.19, a very small coherence here, the 0.19 coherence, but this basically pi phase shift. Why have we got the phase wrong by pi? Well, it actually comes from the fact that we're doing a 2-photon excitation and not a 1-photon excitation. So we're coupling this state, f equals 2, through the p level up to the Rydberg level, but there's also an off-resonant phase shift, AC Stark shift, on the other ground state. And if you keep track of all the phases through the pulse sequence of our gate, you find that there should be a phase shift given by this ratio of quantities, which is just very close to pi. And that's exactly what we see. So this gives us good confidence that we really understand the phase evolution that's occurring here. So to summarize the CNOT results, we have this probability matrix. We create approximations to these Bell states with a fidelity that looks to be just over 1/2. So there's also very recent work from Palaiseau, from Philippe Grandier's group, where they, which is up on the archive, you can look at, and it's a very similar experiment with some differences. They have single atoms and 2 dipole traps, but their traps are very close together, about 3.5 microns, as Pierre said. And because of that, I guess it's hard for them to do different pulses on different atoms, so they collectively excite both atoms and then map them down to the ground state. And that lets them create this B2 state, superposition of 0, 1 plus 1, 0. If you look at their paper, they're claiming a fidelity of 0.75, which puts them deep into the quantum regime. And so you might wonder, why is their experiment working a lot better than this one? And I think it's important at this stage to be clear about what's being achieved and what has not been achieved. And so I'll make the following comment. If you look at their raw data, their fidelity is about 0.46. What they then do is normalize that data by the trace of their experimental density matrix, that is the sum of the probabilities, which is 0.61. When they divide by that, they get their 0.75 fidelity. If we made the same correction to our raw data, we also end up at the same point. So I would say the experiments are actually operating at a very similar level. However, I would not be comfortable making such a correction, because the reason why one has atom loss is in large part due to the fact that you have pulse errors that leave the atoms with an amplitude that's non-zero to be in the Rydberg level. And so the examples of your gate that worked less well have a higher probability of being kicked out of the trap, and therefore you're artificially biasing your results by just dividing by that number. So I would not feel comfortable dividing by that number. I think the reality is the raw data from both experiments is very similar, and I'm sure that in the next couple of years we're going to see much higher fidelity results from all of these experiments, and probably new experiments that will come online. Okay, so let me now, in my remaining time, move on to talking about some developments in optical traps and also going towards arrays. So I described some 2-site experiments. We can put a diffraction grating here and create more sites with our laser beam. We can do a 5x1 array. We can also use this calcite element here to create a 2x5 array. So we've done some experiments recently using this setup. And so we can load single atoms into any one of these sites. The probability of getting loading to all the sites at one time is very small due to the effects that Thad talked about yesterday. We have about a 30% probability into one site, so this scales very badly. We can collect data where we have 3 sites loaded all at once, and we can make composite pictures where we have all 5 sites loaded, but this only happens very, very rarely. I think in a couple days of doing these 5-site loading experiments, the students saw this happen only once or twice. So we really need better loading, and we're working towards that. Nonetheless, we can certainly use these different sites and, for example, drive oscillations on one site while having very low crosstalk at neighboring sites, and so we're interested in doing some multi-qubit gates with this type of setup. There is, however, a problem that we, as I described, have to turn off the trapping laser during the Rydberg excitation and then turn it back on because the trapping laser photoionizes the Rydberg atoms. If we go to a many-site setup, then that's going to be not a good thing to be turning the traps on and off all the time. That's going to give a lot of heating because anytime I do a gate anywhere, I have to turn off all the sites if I can't separately control them. So we'd like to have a trapping potential that works for both ground state and Rydberg atoms. So at the present time, we're using these red detuned traps. The ground states suffer photon scattering and AC Stark shifts. The Rydberg states have negative polarizability, basically free electrons, and they're repelled, and they're also photoionized, and so therefore we have to turn off the trap. And this difference in energies of the trap for the ground state and the Rydberg state atoms also leads to entanglement with the vibrational state, and so that gives loss of coherence. So what we want to do is go to a blue detuned dark trap to improve on these issues. And ideally, this dark trap should have the same polarizability for the ground and the Rydberg states. It's possible to meet that matching criterion. So here's the polarizabilities of some different states versus wavelength. The red line is the ground state scalar polarizability. This dark blue line is a 50D Rydberg level. And you see they cross just to the red of this second resonance excitation line. So this would be a point where we match the polarizabilities. It's actually a very nice point to work. We also almost exactly match the polarizability of the P level, which is good for trapping and cooling. And the vector polarizability, alpha 1, which determines our rate of spin flip changing photon scattering events, is very close to 0. So this is really a super point to work. Unfortunately, it's hard to generate a lot of power there, so we're going to work over at 532 where we have a stronger laser, but that still gives polarizabilities of the same sign in the ground and Rydberg levels. So our approach to making localized traps for ground Rydberg states uses so-called bottle beam. This is inspired by work from Arlt and Paget, although we're doing it in a slightly different way. If I take two Gaussian beams with different wastes and superimpose them pi out of phase and match the intensities, I get a dark spot surrounded by light in all directions. So for example, wastes of 1.5 micron at 532, we get submicron 3D localization, a few hundred nanometers. And then the idea is we also have a Rydberg atom in here, although there's some overlap of a highly excited Rydberg atom with the non-zero intensity areas, we expect that the photoionization will be strongly suppressed. But we need to calculate that in more detail. So we did a demonstration experiment with cesium, tuning close to the D2 line, and we could certainly trap. Our trap time was limited by photon scattering because we were close to resonance. We're now putting together a new experiment. Xiwan Zhang and a visiting student from Johannes from Tillman Fowles group, we're putting together the optics for a green bob trap. And in fact, we've done that, and we can, just to show you the perspectives of this, if we put a diffraction gradient in the output, we can very easily create a 2D array of traps. So this is a 48-site array of dark optical traps. And so the perspective is even with 80% loading efficiency, which we think we can achieve, we'd have a 38 qubit experiment. So that's the kind of direction we want to go in with this. So I'm probably out of time. I had one more thing I want to talk about related to generating multi-particle entanglement, but as I see I guess, how much time do I have? 1 minute. So I'll just say that, I'm going to skip through that and say that another interesting way of manipulating states with Rydberg interactions is to take advantage of the asymmetry that can be present. Supposing I have certain Rydberg levels, S levels, that interact strongly with each other, and also interact strongly with the P levels, but the P levels interact weakly with each other. So an SP transition is dipole allowed, and it scales as 1 over r cubed. SS or PP are van der Waals at long distance, and they scale in this way. So if I take not too high N and large R, there can be a large asymmetry in these interaction strengths. And so that's shown here. For example, at 10 microns, I have close to a factor of 1,000 between the SP interaction and the SS and PP interactions. And we have a protocol for taking advantage of that for creating multi-particle GHZ states. The protocol is shown here, where excitation to S blocks this transfer, and we can calculate the errors involved in that, and the details are in this paper here. And this is really closely related to simultaneous work from the Hans-Peter Buchler and Peter Zoller groups, showing that you can directly create in this way multi-particle entanglement. So these are the things I've talked about: CNOT gate, traps, and just briefly this. Let me just conclude by saying that if you have someone looking for an experimental postdoc in your group, please have them get in touch with me. Thank you.
Questions? myself. I think you mentioned your early error message or estimate in your talk of something like 0.03.
Yeah.
Is this an ultimate limit? How could this be made smaller, or could it be?
That's not an ultimate limit. So that was at n equals 110 microns. If I take n equals 100, the Rydberg atoms are about a micron in size. So if I do my optics better, I can go down to 3 or 4 microns. The blockade interaction is much, much stronger. The limit's below 10 to the minus 4. So, I mean, ultimately, I think one should be able to approach 10 to the minus 4 with these things.
On your measurement on the fidelity, where you actually measured the C1 coefficient, could you also give an error bar on this fidelity measurement? Because you make a fit through these data which have
Let's look at that.
You
so there's the fit.
Large errors on it, so I would guess that the error on the C2 and the C1 is also considerable.
Yeah, so this is the middle of that fit. We are less than 1 sigma away from 0.5, put it that way. So all I can say is our data is consistent with being at the entanglement boundary. We're very close to this boundary now.
I was just wondering on this graph that you have there,
yeah?
There's rather large errors on the data points.
Those are statistical fluctuations.
So how do they enter into this error of the C2 and the C1 and the psi?
So I could change C1, C2, and psi and still draw a line that would pass through these, of course. I get.
A chi-square fit or whatever would give you some errors on that.
Really,
statistical errors.
Of course, but
I would guess that they are rather large because the errors are rather large on these.
Certainly, there's a large uncertainty. I only have 3 data points here, so I can fit a 3-parameter function perfectly, of course. So I can't do a chi-squared here. We are currently taking some more data. Okay.
Because I'm wondering how this enters then into only 1 sigma into the F, I would guess. I mean, just from my...
Matthias, again, I don't quote a sigma because we had 3 points and 3 parameters, so there's no meaning in it. We're taking more data.
Anything else? Yeah.
So actually, can you elaborate a little bit on this atom loss issue? So what, sort of, are you saying that just atoms are left in a Rydberg state?
Yeah.
So you have in total less fluorescence and...
Let me go back to the pulse sequence here, okay? So we drive these pulses, okay? The pulses are not exactly pi pulses. They have some errors in them. And at the end of the gate operation, because of pulse errors, we end up with a state that is not just a superposition of the ground states, but has non-zero amplitude to be in the Rydberg level. We then turn the optical trap back on, and we immediately eject those atoms. And so the gate errors translate into loss of atoms. And if we but I'm saying that normalizing for that is a little bit misleading because those are the lower fidelity events that you're eliminating.
So these experiments, do you have a single shot readout?
Yes, this is the sequence. So we prepare the atoms, we optically pump, we do the pulses, and then we do a single shot readout. So our total losses, let's go back to here, maybe here. Oh, I'm sorry, I'll just stop here. Yeah, so you see we have about 70%. We have about 30% loss, and it was, yeah. But we don't see any evidence for excess intrinsic Rydberg loss. I mean, we can go down, we can drive these 1-atom oscillations between ground and Rydberg, come into the Rydberg state, back to the ground state with close to 100%. So we think it's going to work.
Just following up, the pulse errors that you have are mainly timing errors, or are these also spatial problems like localizing the atoms at the right?
Yeah, there are several factors that contribute. The lasers are not perfectly intensity stabilized. There are pointing errors. The atoms are moving around. They're actually fairly hot. We're doing this with atoms that are about 200 microkelvin. So cooling will help better, but the atoms are moving around and we have focused Gaussian beams. And so we have, depending where the atom is, we see different pulse areas.
All of them contribute.
All of them contribute. So this Monte Carlo simulation I showed earlier for the blockade takes account of all that.
Is there any prospect for cooling those?
Yes, and part of the cooling problem is that when you're working in these dipole traps that have large differential Stark shifts between ground and P levels, it makes the cooling difficult. It sort of messes it up. We're, I think, fairly optimistic that these dark traps are going to work much better as far as cooling goes.
Anything else? Well, let's thank Mark again.